Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we're going to be talking a little bit about complex numbers and how to work with them using polar form. Little bit of review to start. Of course, I is the square root of -1. This is kind of the principal square root if you want to kind of be a little bit more official if we're talking about the definition there. Right? Numbers of this form, so a real number plus I times another real number, a plus bi, these are called complex numbers, right? And we can work with these like kind of normal numbers if you almost think of I as a variable. Well, we already said I was the square root of -1, so I squared should be -1. If we want to add these numbers, well, just like we add a variable together, 1 plus I plus 2 minus I is 1 plus 2, that's 3. I minus I, that's 0, so we just have the number 3. What if we want to multiply these? This is a little bit more complicated, but we can kind of FOIL stuff or square stuff in this case. 1 plus I times 1 plus I, well, if we square this out, it's 1 squared plus 1 times I times 2, so plus 2I plus I squared. Well, I squared was -1, so in fact we have just 2I in this case. Right, and this provides general ways to do this kind of multiplication of the numbers, adding of the numbers there as well. Now, right, in particular, we call these numbers as written in rectangular form here. And so why do we kind of use this word rectangular form? Well, we want to think about this like rectangular coordinates. So if we have a coordinate plane, just like you normally might have an xy plane, here we have this idea of the complex plane. So we kind of have the real parts of the numbers. So you'll sometimes see this as kind of the real part of the plane. And then we have kind of the imaginary part of the plane here as well. But other than that, we kind of think of these things using kind of normal xy coordinates or things like that as well. So, right, if we want to graph some points in kind of rectangular form, in this case, right, if we have some points here, for example, right, this point here is just our normal point 2, right? This looks maybe a little bit weird, but remember 2 is really 2 plus 0i. So this becomes the point 2, 0, and we could graph it as that point right there in the complex plane as well. Right, if we have a point up here, this point here would be 1 plus I, or 1 plus 1i in this case. Right, so if we have a point down here, for example, we could also have this same type of thing happening with a kind of complex only point, right? Only imaginary numbers. This point right here would be kind of -I, which of course we could write as 0 minus I in this case. It's the point 0, -1, and this kind of is now this idea of graphing these complex numbers in what we're calling the complex plane. So, right, this helps visualize things, but we'll see there's some nice tricks that come out of this as well. In particular, we can start using our ideas of different forms of writing coordinates to our advantage. So for example, right, you're pretty used to kind of seeing, okay, we have a point 1, 1. Could we write that point in polar form, right? Where instead of kind of you having 2 points A and B as the X and Y coordinate, we have a kind of radius and an angle or something there, right? So we could write these complex numbers in polar form in this way. So the number a plus bi turns into the number r times cosine theta plus I times sine theta. right? And the wording is slightly different than we would have it in normal kind of polar form. Here we refer to r as the modulus in this case, and theta is what we're calling the argument. So if we have kind of our normal point here, a comma b, let me just draw the quick, this is no different than a kind of polar form equation, right? Then we have this distance right here. This is our r. In complex number terminology, this is our modulus, and kind of theta here is our argument in this case. But it's just the same way you would write a number there in polar form as kind of a normal coordinate as well. Some simple examples here, right? The number 2 we saw before was 2 plus 0i. Of course, that is an angle of nothing. So we could write this as 2 times cosine of 0 plus I times sine of 0. Notice that these things are actually equal to each other. We'll have the advantages of thinking about it in polar form, which we'll see especially a little bit later in this video, but these are kind of straight up equal, right? Cosine of 0 is 1. Sine of 0 is 0. So we have 2 times 0, or we have 2 times 1 plus 0i, which literally is 2 plus 0i. In the same way, right, if we wanted to write this complex number negative I, this is the same as 0 minus I. So this is 1 times cosine of 270, which is 0, plus I times sine of 270, which is negative 1. So we have it written this way. One thing to point out here, right, the pickiness we have in this form is that these angles are the same. Right, so there are different ways of writing this. They're not unique. But one thing you want to keep in mind is if we're talking about the modulus and the argument, you need to use the same angle in both cases. So we could write negative I as 1 times cosine of negative 90 plus I sine of negative 90. That's fine, but you don't want to start mixing and matching different angles in that case. Let's revisit some of the ones from earlier though, and kind of see slightly more complicated ones and how we could write those out in polar form as well. So a good place to start always is, of course, drawing our coordinates. This is a complex number we've already kind of looked at here before in rectangular form. This is our number kind of 1 plus I in this case. And so if we draw out here the radius in this scenario, so we have our kind of radius here. Of course, this is kind of going back then to other calculations we can do in terms of Pythagorean theorem and things like that there, right? There are some formulas for the modulus and stuff that I'll let you guys work out here. But it's easy to always go back to the basics. We have a triangle here. If we draw this down here, we have a right triangle with two sides of 1, and so this is an angle of square root of 2. You probably can recognize this as one of our special triangles. We have a leg of 1, a leg of 1, so this angle is 45 degrees in this case. And this gives us then our polar form of 1 plus I. So the polar form of 1 plus I, let me just kind of write it off to the side here again. Fully here, 1 plus I is equal to, our modulus is square root of 2, and then we have cosine of 45 degrees plus I times sine of 45 degrees. Again, we just have this kind of convention where we write it with the same angle there. So we have one modulus and one argument in this case. Let's do the same thing here for our second example on the screen. So this one has a negative number, so my coordinate plane is going to look a little bit different here. And let me just label the stuff rather than kind of trying to draw it out to scale too much. So we have the point, or the kind of coordinate negative square root of 3 here. We have the coordinate of 1 in this case there. So drawing out our complex number in rectangular form, this is our negative square root of 3 plus I in this case. Now I'm doing simple numbers just to kind of make our lives a little bit easier, but hopefully you see that this type of thing can be done in general. We can draw our kind of hypotenuse out there here as well. We can drop our right angle in this case. We have one side of square root of 3. This one's a little bit more complicated, so let me actually just label these here. So again, Pythagorean theorem gives us a hypotenuse of 2. So we have our modulus is definitely 2 in this case. We have to be a little careful with the argument. This is a mistake sometimes people make. You can again recognize a special triangle here. 1, 2, square root 3. This is giving us our kind of 30-degree angles and 60-degree angles, 30, 60, 90 triangle. This is going to be our 30-degree angle down here. Now the reason we want to be careful is that remember when we're doing these angles and trig angles and stuff, we measure them in polar form from the x-axis going counterclockwise. So we have a 150-degree angle there, and that is our argument. So negative square root of 3 plus I is equal to, we can write this then as, okay, our modulus is 2. And now we have cosine of 150 degrees plus I times sine of 150 degrees. So that is our kind of setup then in this case for converting things into polar form. So we have some examples of 1 plus I. This is then square root of 2 times cosine of 45 plus I sine of 45. Negative square root of 3 plus I, this becomes 2 times cosine of 150 plus I sine of 150 there as well. As always, we want to kind of make sure that our angles kind of match and everything in this case. Now, let's look at one final thing here. Let's look at a simple example again of multiplying in this case. Now on the surface, this is very, very easy, right? This is kind of even easier than the simple example I did at the beginning, right? If we multiply this out here, we pretty clearly get, right, this is just equal to I plus I squared. Well, I squared is negative 1, so this is just basically negative 1 plus I in this case. Now, let's maybe save a little bit of time because this is very, very similar to our 1 plus I here. So rather than 1 plus I, right, we're on the other side. So hopefully everybody is okay rewriting this here in polar form as, again, it's square root of 2. And then we have an angle of 45 degrees, but past the kind of y-axis. So we have a 135 in this case. So we have cosine of 135 degrees plus I times sine of 135 degrees. So, right, this is our negative 1 plus I here, right? So we rewrote this number in polar form and we got this here. Let's take a look a second and see if we can draw some comparisons or patterns, right? We already had 1 plus I is this same type of thing, right? So this was square root of 2 now with an angle of 45 degrees. So cosine of 45 degrees plus I sine of 45 degrees. What about I? Well, that's similar to negative I, except we're now in the kind of positive direction. So this is just a modulus of 1, and our angle is, of course, 90 degrees in this case. So we have cosine of 90 degrees plus I times sine of 45 degrees. Now, let's kind of think here a little bit about the pieces we have and see if we can kind of draw some comparisons from there. So what are the things I want to note here? So note, if we look at the moduluses, what happens for the moduluses? So for the moduluses, we have a final answer of square root of 2. And notice that that square root of 2 we could think of as square root of 2 times 1 in this case. The key thing here is I'm just focused on the moduluses for a second. We have square root of 2, and I want to notice that is square root of 2 times 1 in this case. So we're looking at those and trying to figure out a relationship between those in this case. What if we start looking at the arguments, right? We're starting to look at the angles in this case. So if we have 135 degrees, this is a little bit different, but hopefully everybody sees here that that is 45 degrees plus 90 degrees. So we have a slight interesting thing happening. It doesn't work maybe exactly how we might expect it at the beginning, but this argument here is coming from adding up the different arguments in our kind of original expression there. And whoops, we have a sine of 45 degrees. That should be a 90 there. So let's just fix that quick. And right, good for all of you, right, noticing that in the video, right? Want to keep you guys on your toes every once in a while, whether intentional or not. But it's good to always follow along that way too. So we have 135 is 45 plus 90 in that case here. And right, multiplying these complex numbers was a little bit trickier, right? This was a simple example, but you might have to do FOIL, stuff can get a little bit messy and things like that. But in fact, this always is true. Right? It's actually always true when you work these things. When we're multiplying complex numbers in polar form, you can multiply the moduli. So if we look at our kind of two numbers, r times cosine of theta plus I sine theta times s times cosine of phi plus I sine phi, we multiply those moduli together. And then we add the arguments. So we add those angles together in this case. So we have theta, theta, and then phi, phi. And our final resultant of multiplying these is adding them together in this case. So this is the real power of doing things with polar form for complex numbers. We have a nice way of multiplying. Of course, repeated multiplication is exponentiation. So if we want to raise a number to a complex number to a power, we now have a nice way of doing that too. That is something we'll explore a little bit more in a future video as well. But that is it for today. So check back each Thursday for a new math tidbit. If you liked this video, please subscribe below. Please hit the like button. That helps out a lot. And check out ziml.areteem.org for free daily math practice and a lot of other great resources there as well. Until next time, goodbye.